Hey everyone, welcome to this news story. Today, we turn our eyes to the moon, a world that seems close but hides dangers we can barely imagine. Across its gray surface lie craters, cliffs, and deep shadows that have trapped secrets for billions of years. From the first footprints left by humans to the silent far side we've barely explored, the moon is full of challenges that could make survival nearly impossible. Why did no one ever return after the first missions? What hidden threats lurk beneath the dust, in the shadows, and inside the giant basins that scar the landscape? In this video, we journey across the moon's most dangerous places to uncover the hidden risks that make this world so deadly and reveal why, even today, it remains a frontier few dare to revisit. The moon is Earth's only natural satellite, orbiting at an average distance of roughly 384,400 kilometers. Its size is about one quarter that of Earth in diameter, yet it holds only one-eighth of Earth's mass. This difference in mass directly affects the strength of gravity on its surface. Gravity on the moon is approximately one-sixth that of Earth's, a factor that changes the way objects move and settle. Every step, every fall, and every drop of material behaves differently under this reduced gravitational pull. The surface appears solid and steady, but the low gravity allows particles and rocks to move with less force, creating unique hazards for both humans and machinery. The lunar surface is covered by a layer of regolith, a mixture of dust, broken rock, and small fragments left by billions of years of meteorite impacts. This layer is uneven, often ranging from a few centimeters to several meters deep, and can shift unexpectedly when disturbed. Under the regolith lie larger rocks and bedrock formations. The combination of loose surface material and low gravity means that even small slopes can become unstable. Walking, driving, or landing equipment requires constant attention to the shifting surface. Any miscalculation can lead to a fall or a tip over. The moon has no atmosphere in the way Earth does. There is no breathable air, no wind to move dust or gases, and no protection from extreme radiation. The lack of an atmosphere means that the surface temperature swings dramatically. During lunar daytime, sunlight heats the ground to over 100 degrees Celsius. In contrast, nighttime temperatures can drop below minus 170 degrees Celsius. These swings occur over the course of a lunar day, which lasts approximately 29.5 Earth days. The long day-night cycle exposes equipment and humans to extremes far beyond what is experienced on Earth. Materials expand and contract with the heat, and surfaces can crack or shift under these changes. The absence of air also means that sound does not travel on the moon. Explosions, impacts, or human activity produce no audible effects across distances. Instead, vibrations are transmitted only through direct contact with the surface or objects. This factor adds another layer of danger because collisions or falls may not be immediately noticed unless seen or mechanically measured. Communication relies entirely on radio signals, which must be transmitted between machines, satellites, or Earth. Any interruption in signals can leave explorers isolated in hazardous zones. The moon's surface is heavily marked by impact craters of all sizes. Some are shallow depressions, while others are deep basins hundreds of kilometers across. These craters are often surrounded by raised rims that's made of loose rock and dust. The rims can crumble, creating sudden slides and hidden hazards. The floors of craters may collect fine dust, making the ground deceptively soft and unstable. Shadows in deep craters can extend for kilometers, creating areas where sunlight never reaches. The contrast between light and dark surfaces is sharp, and temperatures in shadowed regions remain extremely low. Equipment and humans must adjust to these changes continuously. The highlands of the moon, often found on the far side, rise above the lower plains known as Maria. These elevated regions are heavily cratered and more rugged than the smoother plains. With steep slopes, jagged ridges, and scattered boulders make traversal challenging. Even small inclines can become dangerous under reduced gravity, as movement is slower to stop and more difficult to control. Any attempt to climb, descend, or maneuver requires precise calculations to prevent slips or collisions with the uneven terrain. Water on the moon is extremely limited. Most of the surface is dry, and any existing ice is found in permanently shadowed craters near the poles. These pockets of ice are valuable for future exploration, but are located in areas that are difficult to access. The scarcity of resources increases the risks for humans, as survival depends entirely on transported supplies. Every drop of water, every unit of oxygen, and every source of power must be accounted for, stored, and protected from environmental hazards. Any failure in supply lines or storage can quickly become critical. Meteorite impacts continue to shape the moon. Small micrometeorites strike the surface constantly, moving at speeds of tens of kilometers per second. These particles are tiny, but carry enough energy to damage equipment or injure an exposed astronaut. Larger impacts, though rarer, leave new craters and redistribute surface material, sometimes in unpredictable ways. The constant bombardment also generates fine dust, which adheres to surfaces electrostatically. Dust can penetrate seals, scratch glass, and interfere with mechanical systems. On Earth, the atmosphere slows or burns up incoming particles, but on the Moon, no. Such protection exists. The regolith itself has unique properties due to long-term exposure to sunlight, radiation, and impacts. Particles are sharp, jagged, and cling to surfaces. When disturbed, the dust can remain suspended briefly, only to settle slowly over time. This property poses challenges for mobility, as the dust can stick to spacesuit joints, wheels, or solar panels, reducing efficiency and potentially causing mechanical failure. Even small accumulations can interfere with sensitive instruments or seals. Engineers and astronauts must account for these properties constantly. The moon's low gravity also affects the way materials fall and settle. Rocks thrown or dropped will move more slowly, but their momentum is harder to stop. Landed spacecraft can sink slightly into soft regolith, altering balance. Rovers must distribute weight carefully to avoid tipping, and astronauts must step cautiously to prevent falls. Every movement interacts with the surface differently than on Earth. Understanding the physical mechanics of lunar soil and rock is crucial for safe exploration and habitation. Temperature, radiation, dust, and gravity all combine to create an environment that is unforgiving. Equipment must be designed to operate under these conditions continuously, with tolerances far higher than those required on Earth. Every component, from life support to structural elements, is exposed to extremes. Even simple tasks, such as moving a tool or walking across a flat area, require careful planning and execution. Failure in any system can have serious consequences. The moon's gravitational field is uneven in certain areas, a result of variations in subsurface density called mascons. These regions slightly alter the path of spacecraft during orbit or descent. Unnoticed, mascons can affect navigation, making precise landing or maneuvering more complex. Engineers must account for these variations when planning missions. Even slight deviations can become dangerous when landing near cliffs, crater rims, or shadowed zones. The lunar environment is shaped by billions of years of geological processes. Ancient lava flows formed smooth plains, while collisions with meteoroids created highlands and deep basins. The resulting landscape is a mixture of flat areas, rugged hills, and sharp depressions. For humans, each type of terrain presents unique challenges. Smooth areas may still conceal hidden dust pockets, while rough terrain can halt movement or damage equipment. The diversity of landscapes requires constant adaptation and situational awareness. Light behaves differently on the moon due to the lack of atmosphere. Shadows are harsh, with near absolute contrast between light and dark. Sunlit surfaces can become blindingly bright, reflecting off dust and rocks. Instruments and cameras must adjust for this variation, and movement within shadows is slower and more careful. Sudden transitions from light to dark can hide hazards, making navigation particularly challenging in cratered regions. The moon's poles present additional difficulties. The angle of sunlight is low, producing long shadows and permanently shadowed craters. These areas can trap cold and ice for billions of years, creating pockets of extreme temperature and potentially hazardous terrain. The combination of darkness and cold requires specialized equipment to operate safely. Even autonomous machines face limitations when sunlight is absent for extended periods. The moon rotates very slowly, completing a full turn approximately every 27.3 Earth days. This slow rotation extends the day night cycle, meaning exposure to heat or cold lasts far longer than on Earth. Extended daylight results in prolonged high temperatures, while extended night exposes surfaces to extreme cold. Surfaces expand and contract under these temperature swings, creating stresses in rocks and regolith. Any stationary structure must withstand these changes without breaking or shifting. In summary, the moon presents a combination of low gravity, extreme temperatures, sharp and shifting dust, constant micrometeorite impacts, uneven terrain, and lack of atmosphere. These factors make it a dangerous place for humans and equipment alike. The environment is predictable in its extremes, but unforgiving in its demands. Every action on the lunar surface must consider physical mechanics, material behavior, and environmental constraints. Human survival and exploration require careful planning, robust engineering, and constant attention to the ever present hazards. These elements form the foundation for understanding why lunar exploration is so difficult and why only a few brief human missions have ever taken place. The combination of physical and environmental factors sets the stage for the moon's most dangerous regions and the challenges that continue to limit human presence. The surface of the moon experiences temperature swings that are far more extreme than those on Earth. The absence of an atmosphere means that heat from the sun is not distributed by air or wind. When sunlight falls on the surface, it is absorbed directly by the regolith and rocks. Daytime temperatures can reach more than 100 degrees Celsius, causing rocks to heat unevenly. Areas exposed to direct sunlight become hot enough to soften some surface minerals, while shaded areas remain much cooler. The difference in temperature between sunlit and shadowed regions can be hundreds of degrees, creating a challenging environment for equipment and human activity. Nighttime brings an entirely different set of hazards. Without sunlight, surface temperatures can drop below minus 170 degrees Celsius. Heat escapes rapidly because there is no air to hold it. Materials that were expanded by daytime heat contract in the cold, causing stress fractures in rocks and dust layers. This rapid change between hot and cold can loosen boulders, crack surfaces, and destabilize slopes. Structures must be able to withstand repeated cycles of expansion and contraction. Electronic systems must function across this extreme range without failure. The day-night cycle on the moon lasts approximately 29.5 Earth days. This extended cycle means that both heating and cooling periods last far longer than on Earth. Exposure to high temperatures can continue for more than a week, while nighttime cold also persists for many consecutive days. For any surface operation, these extended extremes present unique challenges. Solar power may be abundant during the long day, but completely unavailable during the extended night. Thermal control systems must operate continuously, maintaining usable temperatures inside vehicles, instruments, and habitats despite external swings. Regolith, the layer of fine dust and broken rock covering the surface, reacts to these temperature extremes in particular ways. When sunlight strikes regolith, it absorbs energy quickly, heating the top layers more than the material below. The loose particles do not conduct heat efficiently, so shallow surfaces can become hot while the underlying layers remain cool. During the long lunar night, surface particles lose heat rapidly, but the deeper layers retain some warmth. This uneven heating and cooling creates a surface that is both unstable and unpredictable. Machinery driving over the ground can sink slightly or encounter unexpected resistance. Footsteps may disturb hidden layers of dust, revealing loose material that shifts under weight. Rock formations and crater rims are also affected by temperature swings. During the day, rock faces can heat unevenly, creating stresses along natural cracks. Over time, repeated expansion and contraction weaken the structure, causing small fragments to break away. At night, contraction can deepen these fissures. Boulders resting on slopes may loosen and tumble, creating hazards for vehicles or explorers below. Steep, crater walls that appear solid in sunlight can become unstable as temperatures shift. Dust or small stones released by thermal stress can cascade down slopes, posing further risks. The poles of the moon present another variation in temperature extremes. Because sunlight arrives at a low angle, shadows are long and some craters remain in darkness permanently. In these shadowed areas, temperatures can remain below minus 170 degrees Celsius for billions of years. These cold traps collect ice and other volatiles, but they also make the terrain extremely challenging. Any movement into permanently shadowed regions requires specialized thermal protection for equipment and careful planning for stability on surfaces that are both dark and icy. Daytime heating also affects instruments and surfaces differently depending on their material properties. Dark rocks absorb more heat than light-colored rocks. Smooth surfaces reflect some sunlight, while jagged surfaces capture energy unevenly. Solar panels and scientific instruments must be engineered to cope with these variations, preventing overheating and maintaining operational stability. Temperature differences between nearby surfaces can create small airless convection currents in the dust, though these are minimal, yet enough to shift fine particles over time. The combination of long exposure to heat and cold, uneven surface heating, and reactive regolith creates hazards that are often invisible. Loose dust on slopes can act like a soft layer over hard rock, and sudden contact can trigger slides. Small boulders may loosen from repeated thermal stress and move unpredictably. Even a short journey across sunlit terrain can expose equipment to gradual thermal damage. Prolonged exposure for astronauts or machinery can reduce life expectancy, damage electronics, or impair mobility. Temperature swings also influence mechanical performance. Metals expand during daytime heat and contract at night. Joints and fasteners in spacecraft or rovers experience repeated stress. Lubricants can thicken in extreme cold and thin in intense heat, altering performance. Batteries and fuel cells are affected by thermal extremes, requiring insulation or active heating and cooling systems. Failures can occur suddenly if materials or components are not properly protected. Impact craters amplify temperature-related hazards. Their slopes cast long shadows during the lunar day, creating sudden transitions between hot and cold areas. These abrupt changes make it difficult for systems to adapt rapidly. Vehicles moving from sunlight into shadow can experience temperature drops of more than 100 degrees in seconds as at the surface layer. Shadows may hide loose dust or unstable rocks, adding another layer of hazard. Ridges and rills on the moon are particularly vulnerable to temperature stress. Narrow crevices may trap heat or cold in unexpected ways. Sunlight can warm one side of a rill, while the opposite side remains extremely cold. This uneven heating can weaken rocks, dislodge boulders, and disturb the stability of nearby slopes. Thermal stress over billions of years has shaped much of the current surface, leaving patterns that continue to affect movement and safety. During lunar daytime, surfaces facing the sun can reach temperatures sufficient to affect human skin through spacesuits if not properly insulated. Materials that are safe under moderate heating can degrade over prolonged exposure. Shadows offer cooler conditions, but may conceal hazards like dust filled pits or loose stones. The contrast between light and shadow is therefore both a thermal and a physical concern, influencing every aspect of movement, equipment operation, and observation. Dust on sunlit surfaces behaves differently from dust in shadow. Fine particles can become charged by sunlight and radiation, sticking to equipment surfaces. Electrostatic attraction increases as dust moves from cold, shadowed areas into heated, sunlit zones. The result is accumulation on critical parts, potentially blocking joints, instruments, or sensors. Repeated cycles of heating and cooling exacerbate this effect, slowly but steadily degrading efficiency over time. Even stationary structures, such as landers or scientific instruments, must contend with temperature induced stress. Legs, panels, and supports expand during the day and contract at night, creating slow shifts in alignment. Over multiple lunar cycles, these movements can destabilize foundations, tilt sensitive instruments, or fracture materials. Engineers designing for the lunar environment must consider the long term impact of repetitive thermal cycles on both mechanical and electronic systems. The extreme range of temperatures also affects exploration planning. Routes must consider which areas are sunlit, so which remain in shadow, and which transition between conditions rapidly. Tasks requiring delicate operation or stability are scheduled according to thermal conditions. Even robotic exploration relies on predictive models of heating and cooling to avoid overheating, freezing, or structural stress. Understanding these cycles is essential to prevent accidents and maintain operational capability. In all, the extreme swings of temperature on the moon are a constant pervasive hazard. They influence the stability of surface materials, the performance of equipment, the integrity of structures, and the behavior of dust. The long day night cycle prolongs exposure to both heat and cold, while local variations in terrain create uneven conditions. Thermal dynamics combine with gravity, dust, and terrain to form a complex environmental system that is unforgiving to unprepared machines or humans. The moon's regolith, terrain, and shadow patterns interact continuously with sunlight to shape an environment defined by extremes. Daytime heat softens surface layers, nighttime cold hardens and contracts them. Crater floors, slopes, and riles respond differently to these changes, producing unpredictable hazards. Equipment and structures must absorb these stresses over long periods, while explorers must navigate constantly shifting and dangerous surfaces. Thermal extremes, combined with other environmental factors, form one of the primary reasons why the moon remains a difficult place for humans to occupy. Even in areas that appear flat or safe, the interaction of sunlight, shadow, regolith, and rocks creates hazards that are both subtle and significant. Understanding and managing these temperature swings is fundamental to safe operation, planning, and the long term presence of any mission on the lunar surface. The surface of the moon is heavily scarred by impact craters of all sizes. Each crater is a result of a collision with a meteoroid, asteroid, or comet. These collisions occur at extremely high speeds, often tens of kilometers per second. When an object strikes the lunar surface, the energy released is immense, displacing rock and soil and forming a depression surrounded by raised rims. Over billions of years, this process has shaped nearly every part of the moon's landscape. Craters vary greatly in size, from tiny indentations a few meters across to massive basins hundreds of kilometers in diameter. The formation of a crater begins with the impactor striking the surface. The kinetic energy of the moving object is converted into heat, pressure, and shock waves that propagate through the regolith and bedrock. These waves fracture the surrounding rock, eject debris, and create a circular depression. Larger impacts may penetrate deeply into the crust, while smaller ones affect only the surface layers. The ejected material forms the rim and surrounding ejecta blanket, which can spread for several crater diameters. The texture of these ejecta zones is uneven, with rocks of various sizes and fine dust scattered widely. Crater walls are often steep and jagged. The angle of the walls can range from gentle slopes to near vertical cliffs, depending on the size and age of the crater. Newly formed craters tend to have sharper, more pronounced rims, while older craters erode gradually under repeated impacts and thermal cycles. Loose rocks, broken regolith, and dust cover the slopes, creating a constantly unstable environment. Even minor disturbances, such as windless vibrations or mechanical movement, can trigger small slides of material. These slides may appear small, but can accumulate over time, creating hidden hazards for anyone or anything moving near the edge. Shadows within craters present additional dangers. Deep craters often contain regions that remain in permanent shadow. Sunlight may never reach the bottom, leaving temperatures extremely low, well below the already harsh averages of the lunar night. Surfaces in shadowed regions can be coated with fine dust, loose rocks, or hidden ice in polar craters. Visibility is limited, making it difficult to detect unstable areas or sudden drops. The edges of shadows can change drastically over the course of a lunar day as sunlight moves across the landscape, revealing some hazards while concealing others. The depth of craters varies greatly. Small impacts may create depressions only a few meters deep, while large basins can extend several kilometers downward. The floor of a crater may be uneven, filled with rocks, dust, or collapsed material from the walls above. The bottom can be deceptively smooth in some areas, hiding loose material beneath a thin surface layer. A small misstep can cause a person or rover to slip, sink, or slide toward deeper parts of the crater. Gravity, while weaker than on Earth, still pulls objects steadily down slopes, making even moderate inclines risky. Rim stability is a critical concern. Ejected rocks and dust create loose formations that may crumble under pressure. Crater edges can shift gradually due to thermal stress, small impacts, or vibrations. Over time, repeated stress fractures in the walls weaken the structure. This makes it possible for material to fall unexpectedly, even without external contact. Steep walls are especially dangerous because loose rocks can tumble down, striking surfaces or equipment below. A careful approach is required to navigate these areas safely. The size and density of craters influence their surrounding terrain. Large impacts can create secondary craters, formed when ejected debris strikes nearby areas. These smaller craters further disrupt the landscape, producing jagged terrain that complicates movement and planning. The irregularity of this terrain can affect trajectories, vehicle stability, and structural support. Any path through cratered regions requires constant evaluation of surface stability and the risk of unseen obstacles. Craters often intersect with other features on the lunar surface. Some overlap older craters, creating ridges and walls that are uneven and fragmented. When multiple craters intersect, the resulting topography can be unpredictable. Slopes may be inconsistent, with sudden drops or rises that are difficult to detect. The combination of depth variation, loose material, and sharp changes in elevation makes these overlapping regions particularly hazardous for surface operations. Erosion on the moon occurs primarily through repeated impacts and thermal cycling rather than water or wind. Over time, crater walls may slough off material in small slides or larger collapses. Fine dust and loose rocks gradually migrate downward, filling lower areas or collecting in pockets. Some areas become stable only after long periods, while others remain fragile. These ongoing processes continuously reshape craters, maintaining a dynamic and potentially dangerous environment even billions of years after the initial impact. The angles of crater walls influence how sunlight interacts with the surface. Sunlit slopes heat rapidly, while shadowed sides remain cold. Temperature gradients can expand and contract rocks differently across the wall, weakening structures over time. Thermal stress can loosen fragments that were stable for millions of years, creating sudden hazards. Shadows can hide these areas entirely, making visual detection difficult. Navigation and planning must consider these thermal effects, in addition to physical slopes. Crater floors can contain unusual surface materials. In some basins, fine dust settles densely, producing soft, powdery areas that behave like quicksand under mechanical pressure. In others, larger rocks and boulders dominate, producing uneven terrain that is difficult to traverse. Water ice may be present in permanently shadowed craters near the poles, creating both potential resources and extreme obstacles due to cold and slippery surfaces. The combination of material variation and surface instability means that even seemingly simple areas can conceal serious risks. The walls of craters may include terraces or ledges formed by slumping of the initial crater rim. These terraces can be deceptive, appearing solid while being supported only by loose regolith. Any weight applied to the edge can trigger collapse, and small slides can cascade downward. Over long distances, falling rocks may travel hundreds of meters, threatening nearby equipment or exploration zones. The weak cohesion of regolith on slopes amplifies these effects. Impact craters also affect gravitational distribution locally. Mascons, or regions of higher density material beneath the surface, are often associated with large basins. These variations slightly alter local gravity, influencing the movement of objects and the trajectory of spacecraft near the surface. Small miscalculations in landing or maneuvering can push vehicles or rovers toward crater edges or slopes, compounding physical hazards with navigational challenges. The interior of some craters may include central peaks or uplifted rock formations. These features form during the rebound phase of a large impact. Central peaks are often jagged, steep, and unstable. They may rise several kilometers above the surrounding floor, presenting obstacles for traversal. Loose rocks and fragmented regolith on these peaks increase the risk of slides or sudden falls. The combination of height, slope, and instability makes them particularly dangerous to approach. Craters intersect with other geological features, such as rills, lava tubes, and fault lines. These intersections create irregular terrain that is difficult to predict. Slopes may shift unexpectedly, and hidden voids may exist beneath the surface. The combination of geological complexity, loose material, and sharp contrasts in temperature and shadow makes cratered regions among the most hazardous areas on the Moon. Smaller craters, though less dramatic in size, still present challenges. They often have steep sides relative to their diameter and contain loose dust that can obscure the true slope. Rovers, or humans moving across these areas, may find footing unstable, equipment may sink into soft layers, and sudden slides are possible. Even seemingly minor craters contribute to the cumulative hazard of lunar navigation. Overlapping impacts produce chains or clusters of craters, amplifying risk. Movement through these zones requires constant evaluation of slope stability, dust depth, and shadowed regions. The combination of steep walls, uneven floors, loose material, and temperature effects creates a dynamic system where hazards evolve slowly but continuously. Equipment and humans must adapt constantly to these changing conditions. Cratered terrain near the poles is especially challenging. Shadows remain long and in some areas never receive sunlight. Temperatures remain extremely low, and fine dust mixed with ice produces surfaces that are both soft and slippery. Navigation in these areas requires careful analysis of slope, material, and potential ice coverage. Mistakes can result in falls, equipment failure, or loss of stability. The moon's craters are a record of billions of years of impacts, yet they also serve as a living hazard. They are continually reshaped by micrometeorite impacts, thermal stress, and slow movement of regolith. Even areas that appear safe can conceal sharp drops, loose rocks, or deep dust layers. The combination of steep walls, unstable rims, shadowed floors, and variable material properties makes them among the most dangerous regions for exploration. In conclusion, impact craters form the backbone of the moon's hazardous terrain. Their formation, structure, and ongoing evolution create steep walls, unstable slopes, and shadowed regions that present constant risk. They illustrate how the combination of lunar gravity, regolith properties, and thermal extremes produces a complex system of hidden dangers. Understanding craters is essential for assessing lunar safety and planning any operation on the surface. The distribution, scale, and nature of craters reveal why the moon is not only visually scarred, but physically challenging for humans and machinery alike. The moon rotates slowly, completing one full turn approximately every 27 and a third Earth days. This slow rotation results in the same side of the moon always facing Earth. The side that remains hidden is called the far side, while the side visible from Earth is called the near side. The far side has a markedly different landscape from the near side. Unlike the near side, which is dotted with large, smooth plains called Maria, the far side is dominated by highlands and rugged terrain. Large basins and deep craters cover much of the surface, giving it a heavily scarred and uneven appearance. Maria on the near side are basaltic plains formed by ancient volcanic activity. These areas appear darker and smoother than surrounding terrain. The far side, however, contains very few Maria. Its crust is thicker and more resistant to volcanic flows, so the surface did not develop large, flat plains. Instead, the far side presents highlands that rise above the average surface level. These regions are composed mainly of anorthosite rock, which is lighter in color and more reflective than basalt. The highlands are heavily cratered with overlapping impact structures that create jagged ridges and uneven floors. The lack of Maria on the far side results in a landscape with more elevation variation. Crater walls and mountain like ridges rise sharply from the surrounding areas, creating steep slopes and hidden depressions. Valleys and rills cut across some regions, but these are less extensive than the lava formed channels on the near side. The highland surfaces are covered with thick regolith, similar to the near side, but the slopes and angles of terrain can be more extreme. Loose rocks, sharp debris, and shifting dust are common hazards across these highland regions. The far side's topography also influences sunlight exposure. Large craters and elevated ridges cast long shadows, and many shadowed regions remain in darkness for extended periods. Thermal extremes are amplified because some areas receive sunlight at oblique angles only, while others remain shaded for much of the lunar day. This combination of steep terrain and uneven lighting makes navigation more complex and increases the risk of equipment or human movement on the surface. Exploration of the far side presents a significant challenge for communication. Because it faces away from Earth, radio signals cannot travel directly between the far side and mission control. Any spacecraft or rover operating in these regions requires a relay system, typically involving satellites positioned in lunar orbit or in specific locations to transmit signals. Without such a relay, operations would be effectively blind, making navigation, data transmission, and emergency coordination nearly impossible. The lack of direct communication adds a layer of risk. Without immediate confirmation from mission control, autonomous systems or crew must rely on pre-programmed instructions or local decision-making. Delays in signal transmission increase the difficulty of responding to hazards such as unstable slopes, shifting dust, or unexpected impacts. Any miscalculation in movement or timing could result in accidents that cannot be corrected quickly. Large impact basins dominate the far side, such as the South Pole Aitken Basin, one of the largest known craters in the solar system. It spans approximately 2,500 kilometers in diameter and reaches depths of up to 13 kilometers. The size of these basins produces extreme slopes, long shadowed areas, and complex crater floors with secondary craters, fractures, and boulder fields. The terrain is irregular, and navigation across the basin requires careful assessment of slope stability, surface materials, and shadow conditions. The far side is also more heavily cratered than the near side, with fewer maria to cover or smooth the surface. Ancient impacts remain exposed. Some regions contain overlapping craters, creating jagged ridges and uneven floors that complicate movement. Smaller craters, while less noticeable from orbit, can still contain soft dust, loose rocks, and steep walls, increasing hazards for landers or rovers. Volcanic activity on the far side was limited, resulting in thinner lava flows and fewer basaltic plains. The lack of volcanic smoothing preserves the older, rugged landscape. The surface is more prone to abrupt terrain changes, hidden depressions, and unstable regolith layers. Exploration equipment must be designed to handle these sudden changes in elevation, as simple flatness cannot be assumed over long distances. The far side's highlands are composed of light-colored anorthosite, which is more reflective than basalt. This affects how sunlight interacts with the surface. Sunlight reflecting off highland rock can create intense brightness in certain angles, while nearby, shadows remain very dark. These sharp contrasts complicate visual navigation and instrument calibration. Cameras, sensors, and optical systems must adjust to extreme brightness differences to avoid misreading terrain features. Shadowed regions on the far side are particularly hazardous. The combination of low-angle sunlight and deep basins creates areas where light never reaches the surface. Temperatures remain extremely low, and fine dust may be compacted unevenly or mixed with ice at polar latitudes. Movement in these regions is challenging due to reduced visibility and unpredictable surface stability. Both humans and robotic explorers must rely on careful mapping and pre-planned routes to avoid these dangers. The thickness of the crust on the far side also influences surface stability. In some locations, subsurface variations can create uneven support for surface material. Loose regolith may cover weak rock layers, and small disturbances can trigger slides or collapses. These conditions make planning for landings and traverses more complex, as the risk of shifting surfaces is higher than on the near side. Navigation over far side terrain must account for elevation, crater density, and slope angles. Even relatively small inclines can become dangerous due to loose dust and low gravity. Equipment must be capable of adjusting to these conditions continuously. Wheels, legs, or treads may sink or slip unexpectedly, and sudden movements can trigger cascading debris from higher slopes. Detailed analysis of topography is essential for safe movement across these highlands. The far side's isolation affects scientific operations as well. Sampling requires precise coordination because materials must be collected and transmitted back via relay satellites. Delays in communication can affect the timing of operations, including sample handling, instrument deployment, and equipment repositioning. Any error in handling or movement could result in damage or loss of critical data. Some of the far side's basins also contain small, flat areas within their depths, formed from ancient lava flows or impact melt. These areas are exceptions to the generally rugged terrain, but even here, hidden dust pockets or soft regolith may conceal hazards. Rocks from previous impacts may remain partially buried, creating obstacles that can affect landing stability or mobility. Even the smoothest looking plains on the far side require careful assessment before equipment or personnel traverse them. The interaction of terrain, slope, regolith, and shadows defines the hazards of the far side. Slopes may appear stable in one angle, but shift under weight. Dust may conceal boulders, and shadows may hide sudden drops. The combination of steep highlands, cratered basins, and communication challenges creates a unique set of dangers compared to the near side. The far side is visually striking, yet each visual element can represent a hidden risk to exploration. Temperature extremes also differ slightly on the far side due to elevation and exposure. Highlands rise higher than nearby Maria, absorbing sunlight differently. Elevated regions may experience slightly higher temperatures during lunar day and more rapid cooling at night. The interaction of sunlight, shadow, and regolith affects thermal behavior, adding complexity to planning surface operations. Equipment must be protected against both direct heating and prolonged cooling in shadowed areas. The South Pole region on the far side is especially notable. It contains permanently shadowed craters that are extremely cold and potentially harbor water ice. Ice deposits create both opportunities and hazards. Traversing these areas requires careful control of temperature, stability, and weight distribution. Even robotic rovers must move slowly and deliberately to avoid tipping or sliding on icy dust layers. Exploration of the far side is possible only with orbital support or relay satellites. Missions must account for delays in command and data transmission. Any movement or experiment must be pre-planned to avoid unexpected terrain hazards. The combination of rugged highlands, cratered basins, shadowed zones, and communication constraints makes the far side among the most challenging areas for human and robotic activity on the Moon. In summary, the Moon's far side presents a landscape dominated by highlands, steep slopes, and heavily cratered basins. The scarcity of Maria leaves terrain uneven and jagged. Shadows are long, communication with Earth is limited, and surface stability is unpredictable. Navigation, landing, and exploration are inherently more hazardous than on the near side. The far side illustrates how geological history, surface composition, and isolation combine to create extreme environmental challenges, reinforcing why human presence has remained concentrated on the near side to this day. The Moon's surface is not uniform. Beyond craters and highlands, it is crossed by long channels called rills. These rills appear as narrow grooves, sometimes straight, sometimes winding across the terrain. They form through volcanic or tectonic activity. Some rills are collapsed lava tubes, where molten rock once flowed beneath the surface and the ceiling later fell in. Others result from surface fractures or tectonic stretching that pulled the crust apart. The variation in formation leads to differences in width, depth, and stability. Rills can extend for tens or even hundreds of kilometers. The largest ones are several kilometers wide and hundreds of meters deep. Some follow relatively straight paths, while others meander, twisting and turning across plains or between cratered highlands. Their walls are often steep and composed of loose rock, regolith, and fractured bedrock. Dust collects along these walls, creating uneven surfaces that can shift under weight. Rills may contain hidden pits or depressions, making navigation hazardous for vehicles and humans. Canyons on the Moon, though less common than on Earth, also present significant risks. Some large impact basins are bordered by canyon-like ridges or terraces formed by collapsing crater walls. These can range from hundreds of meters to several kilometers across and contain abrupt drops. Walking or driving across the edges requires careful consideration of slope stability, loose rocks, and regolith depth. Even minor disturbances can trigger slides or collapses. Lava tubes are particularly significant as both geological features and hazards. These are tunnels formed when the surface of a lava flow cooled and solidified while molten rock continued to move beneath. Once the lava drained, a hollow tube remained. Some tubes extend for dozens of kilometers and may be tens of meters wide. The ceilings of these tubes can collapse over time, leaving a jagged, unstable surface. Hidden voids beneath the regolith create the potential for sudden falls or equipment loss. The structure of a lava tube is often deceptive. From the surface, the tube may appear solid, but its roof may be thin in sections. Collapse may occur naturally due to thermal stress, micrometeorite impacts, or gradual weakening of the rock. Small cracks can widen, and portions of the ceiling may fall without warning. Any attempt to traverse such areas requires precise mapping and caution. Unseen openings in the surface may be hidden by dust or small debris, making detection difficult without advanced scanning instruments. Rillas, canyons, and lava tubes often intersect with other features. They can cut across crater floors, highland ridges, or maria. Where rills follow a slope, loose dust and debris may accumulate at the bottom, forming soft layers that can shift when pressure is applied. Lava tube entrances may be partially blocked by collapsed rock or ejecta from nearby impacts. This creates an environment where hazards are hidden until directly approached. The scale of these features is important for understanding their dangers. A narrow rill, only a few meters wide, may be a simple trench, but longer, deeper rills can trap vehicles or equipment if they are misjudged. Lava tubes of significant width can hide drop-offs of tens of meters. Canyons, in some cases, expose cliffs and terraces that are hundreds of meters high. Movement across or near these features requires constant evaluation of footing, slope, and material stability. Shadowing within rills and canyons adds to hazards. Sunlight may illuminate only one side of a rill, leaving the opposite wall in deep shadow. Temperature differences between light and dark surfaces create thermal stresses, loosening rock and regolith. Dust in shadowed areas can behave differently, remaining soft or electrostatically charged, increasing the risk of slips or equipment interference. Shadows may also conceal holes or cracks in lava tube ceilings. The presence of regolith complicates traversal further. Dust layers can conceal hard rock, soft material, or cavities beneath. When disturbed, particles may slide or collapse into hidden voids. A rover's wheel may sink unexpectedly, or an astronaut may encounter a loose patch that gives way. Even small disturbances can trigger cascading falls of dust or rocks from rill walls or canyon edges. Repeated thermal cycling over billions of years weakens surfaces, making the environment unpredictable. Lava tubes may also contain secondary features, such as skylights, holes in the roof that expose the interior to the surface. Skylights can be several meters across, and the edges are often fragile. Approaching too closely may cause collapse, and material inside may be unstable. While these formations provide potential shelter for future missions, they also represent serious hazards for unprepared explorers or machinery. Exploration within rills and lava tubes is complicated by low gravity. Objects fall more slowly, but momentum is harder to stop, increasing the risk of sliding or tipping. Loose rocks may continue to move after initial contact, spreading hazards along the channel. Equipment must be stabilized carefully, and any movement must account for potential cascading effects of disturbed material. Temperature variations further affect these features. Sunlit walls of rills or canyon slopes can heat rapidly, while shadowed portions remain cold. The resulting expansion and contraction of rock may dislodge material gradually over time. Lava tube ceilings may crack from these stresses, and relay walls may shed small rocks onto their floors. Dust inside tubes can shift slowly, creating soft areas that conceal harder rock beneath. The complexity of terrain also affects navigation. Long rills may wind across plains, rising and falling with minor slopes that are difficult to detect from a distance. Lava tubes can extend for kilometers without obvious entrances or exits, making mapping essential. Canyons may contain terraces and ledges that are invisible from above, with steep drops hidden behind walls. Detailed topographical information is necessary to predict hazards and plan safe traversal. The moon's geological history contributes to the formation of these features. Lava flows from ancient volcanic activity created many rills and tubes. Tectonic stretching and subsidence formed fractures and canyons. Impact events modified existing structures, leaving debris and secondary craters that intersect with rills and tubes. The resulting surface is a patchwork of hazards shaped by multiple processes over billions of years. Rills, canyons, and lava tubes may contain dust and rocks displaced by past impacts. Fine material settles along floors and walls, creating soft layers that can shift under pressure. Larger rocks may be embedded in the regolith or partially exposed, increasing risk for exploration equipment. Subsurface voids may exist where the regolith covers collapsed tube sections or hidden cavities. These features make any movement unpredictable and require careful planning. The structural stability of these formations is variable. Some rilly walls and lava tube ceilings are stable over long distances, while others contain thin rock that can fail unexpectedly. Canyons formed from collapsed crater rims may have terraces that give way when weight is applied. Continuous monitoring of terrain stability is essential for safe operations, particularly when moving heavy equipment or deploying instruments. The combination of scale, shadow, temperature, and regolith behavior creates a complex hazard system. A long rill may have sections that appear safe but contain hidden voids, loose dust, or fragile rock. Lava tubes can harbor large drops inside their interiors, while canyons may include terraces and slopes that are difficult to detect until approached. These elements demand careful assessment before movement or deployment of equipment. Dust in these environments behaves uniquely. Fine particles cling to surfaces electrostatically, especially in shadowed or cold areas. When disturbed, dust may flow like a soft layer over hard surfaces or accumulate in depressions. This movement can mask small rocks or voids, creating hidden hazards for vehicles and humans alike. Repeated thermal cycles exacerbate the instability of these dust layers, making repeated passes across rills or tubes unpredictable. Lava tube skylights and collapsed sections may serve as potential shelters for future lunar exploration, but accessing them safely requires knowledge of the surface and subsurface structure. Small cracks or thin rock sections can collapse under weight, and regolith covering hidden voids can shift unexpectedly. Even a small misstep may lead to falls or damage to equipment. In summary, lunar rills, canyons, and lava tubes form a network of hazards across the moon's surface. Their formation through volcanic activity, tectonic movement, and impact processes has created steep walls, hidden voids, loose regolith, and variable stability. Temperature extremes, shadowing, and dust behavior amplify these dangers. Navigation, landing, and movement within these features require careful assessment, constant monitoring, and robust engineering to prevent accidents. They are among the most complex and hazardous regions for exploration on the moon. The surface of the moon is covered by a layer of fine, broken rock called regolith. This layer formed over billions of years through repeated impacts from meteoroids and the gradual breakdown of surface rocks. The regolith varies in thickness, from a few meters on older Maria to tens of meters in highland regions. Its particles are jagged and irregular, unlike most earth sand, which is smoothed by water and wind. These sharp edges make the regolith highly abrasive and potentially damaging to equipment. The dust in the regolith is extremely fine, sometimes less than a few micrometers in diameter. This fine dust can infiltrate tiny crevices, coating mechanical joints and sensitive electronics. Rovers, landers, and suits are all affected by the persistent intrusion of dust particles. The sharpness of the dust can wear down metals and polymers over time, creating gradual degradation that can compromise the reliability of critical systems. Wheels, bearings, hinges, and seals all face continuous abrasion from contact with lunar dust. Electrostatic charging is another significant property of the dust. The moon has no atmosphere to shield the surface from the sun's ultraviolet radiation or from the solar wind. As sunlight strikes dust particles, they can acquire an electric charge. Charged dust can stick to surfaces, including suits, visors, solar panels, and instruments. Over time, this adhesion increases, creating layers of fine particles that are difficult to remove. Dust accumulation can reduce the efficiency of sensors, block joints, and interfere with optical systems. The adhesion of dust is not limited to surfaces exposed to sunlight. In shadowed regions, particles can cling due to static charges built up over time. Movements such as walking, driving, or equipment operation can dislodge dust, creating clouds of suspended particles that resettle in unpredictable patterns. Even slight vibrations or mechanical activity can spread dust into previously clean areas, increasing long-term contamination risks. Regolith particles are hard and angular because they have never been weathered by water or wind. When equipment moves across the surface, these sharp edges act like tiny cutting tools. Tires, treads, and moving parts can experience accelerated wear. Repeated exposure over multiple missions would require regular maintenance, replacement of worn parts, or careful design of dust-resistant mechanisms. Materials used must be selected for hardness and resistance to abrasion, yet even these can degrade gradually under continuous contact. Dust infiltration is also a hazard for human exploration. Lunar suits must prevent particles from entering joints, gloves, or seals. Sharp dust can scratch or puncture flexible layers, gradually weakening their protective ability. Visors and helmet optics may be scratched or coated with dust, reducing visibility. Internal systems, such as life support or cooling lines, may be affected by dust contamination if it penetrates through seals or joints. Any exposure increases maintenance requirements and potential risks to long-duration missions. The behavior of regolith under mechanical stress is unpredictable. Fine dust can act like a fluid when disturbed, flowing into low areas or forming soft layers over hard rock. Loose particles on slopes or near crater edges may slide unexpectedly, shifting weight or movement paths. Even small disturbances can trigger localized avalanches of dust and small rocks. These behaviors combine with low lunar gravity, making the material slower to settle yet still capable of destabilizing equipment or humans traversing the surface. Electrostatic forces can create small levitation effects in dust. Particles may rise slightly from the surface when charged by sunlight or solar wind, then settle gradually over hours or days. This slow movement can allow dust to infiltrate areas previously protected. Over time, even areas not directly exposed to movement can accumulate fine particles. Sensitive instruments, cameras, and mechanical joints are particularly vulnerable to this slow accumulation. Regolith's thermal properties also contribute to its hazards. During the long lunar day, surface dust heats quickly, while underlying layers remain cooler. During the night, the surface cools rapidly. This uneven expansion and contraction can loosen particles, increase dust mobility, and gradually erode surfaces. Dust layers on equipment or structures may experience small shifts, creating abrasive movement between parts or weakening adhesion to protective coatings. Repeated mechanical exposure further alters the surface. Rover wheels, footsteps, and landing thrusters disturb the regolith, kicking dust into the surrounding environment. This movement produces temporary clouds of fine particles that settle slowly over time. In areas with repeated traffic, dust may accumulate unevenly, forming soft patches or depressions that can affect stability. Even small undulations in surface layers can conceal hazards such as hidden rocks or voids. The cumulative effect of dust and regolith is a long term mechanical risk. Parts exposed to repeated abrasion may fail gradually, and systems may lose efficiency. Electrical contacts may degrade due to fine particle accumulation. Optical instruments may experience scattering or blockage from adhered dust. Any human mission must plan for frequent cleaning, inspection, and potentially replacement of parts to maintain operational safety over extended periods. Dust also interacts with equipment design in subtle ways. Hinges, sliding panels, and rotating components must account for particle intrusion. Filters may clog, seals may wear, and lubricants can become contaminated. Even hardened metals may show slow wear over multiple exposure cycles. These effects are not always immediately visible, but accumulate over time, gradually reducing the reliability of machines and instruments. Lunar dust has a low cohesion, but when disturbed, it can act unpredictably. Loose particles on slopes or crater edges may shift under small loads, creating microslides that destabilize equipment. Footsteps or rover tracks leave impressions that reveal loose layers beneath more compacted dust. Movement across these areas must account for sudden changes in surface stability, particularly near slopes, rills, or crater edges. Dust accumulation can be accelerated by sunlight and radiation. Surfaces exposed to direct light tend to attract more electrostatically charged particles. Over time, this can create uneven distribution of dust on vehicles, suits, and instruments. Accumulated dust can interfere with heat dissipation, optical clarity, and mechanical performance. Careful monitoring and mitigation strategies are required for long term operation. Okay. Regolith's interaction with mechanical systems is compounded by lunar gravity. At 1/6 the strength of Earth's gravity, dust behaves differently when displaced. Particles travel farther, settle more slowly, and can remain suspended longer after disturbance. This affects landing zones, mobility, and surface operations. Loose dust may adhere to wheels, treads, or boots, increasing the risk of sliding, clogging, or material transfer across surfaces. Even static structures are affected. Landers, instruments, and deployed equipment accumulate dust over time. Abrasive particles that can degrade coatings, scratch surfaces, and block sensors. Solar panels may lose efficiency due to adhered dust, requiring mechanical cleaning or protective designs. Long term exposure to regolith is a key factor in mission planning, influencing both material selection and operational protocols. Fine dust may also pose challenges for future habitats. Airlocks and suit ports must prevent infiltration. Even minimal dust penetration can accumulate within enclosed environments, creating maintenance issues and potential hazards for crew members. Protective measures must address both mechanical wear and human health concerns, though toxicity and inhalation risks are separate from mechanical degradation. In addition to abrasiveness, dust affects thermal performance. Layers of regolith on instruments or structures may insulate surfaces differently, altering expected heating or cooling rates. This can create uneven thermal expansion, stressing joints or moving parts. Repeated cycles of heating, cooling, and dust accumulation gradually reduce structural stability and mechanical efficiency. Dust movement is also influenced by subtle surface vibrations. Thruster firings, lander settling, or rover wheels can dislodge particles that shift across surfaces, slowly covering instruments or creating soft layers over harder substrates. The slow, persistent movements make long term planning for mobility and equipment stability essential. Overall, the regolith layer and its fine dust represent continuous hazards. Their sharp, abrasive nature, combined with electrostatic adhesion and low cohesion, creates a dynamic surface that can erode, destabilize, and interfere with equipment and humans. Long term exposure gradually compromises mechanical systems, thermal management, and optical performance. Understanding and mitigating these risks is critical for safe and sustained operations on the lunar surface. The moon's surface is constantly exposed to small meteoroids, called micrometeorites, striking at high speeds. Unlike Earth, the moon has no atmosphere to slow or burn up these particles. On Earth, many meteoroids break apart or vaporize before reaching the ground. On the moon, there is no such protection. Even tiny particles, smaller than a millimeter, hit the surface with the full speed of their orbit, often tens of kilometers per second. When a micrometeorite strikes, it penetrates the regolith and sometimes the bedrock beneath. The energy released is concentrated in a very small area, causing local melting or vaporization of surface material. Tiny craters form with every impact. Although these craters are small, they appear across the moon continuously, adding to the roughness and complexity of the terrain. Over millions of years, the surface becomes a patchwork of these countless tiny scars. Larger micrometeorites can dig deeper into the regolith. Even small rocks or metallic fragments can punch holes into spacecraft shields or protective layers of suits. Repeated strikes gradually wear down exposed materials. Metal surfaces may show pitting, coatings may flake, and glass or ceramics may develop microfractures. These cumulative effects increase hazards for equipment over time, especially on missions that remain on the surface for extended periods. The lack of atmosphere also affects the distribution of ejecta from impacts. When a micrometeorite hits the surface, it ejects small particles in all directions. On Earth, most small debris would be slowed by air resistance. On the moon, these particles travel further before settling, landing on nearby equipment, instruments, or structures. Even distant impacts contribute to a slow but persistent accumulation of fine debris across surfaces. Micrometeorite impacts occur constantly, day and night. The moon receives particles from interplanetary space, some from comet tails, and others from asteroid fragments. The flux of particles is continuous but variable, with occasional increases during meteor showers or near certain orbital intersections. Over time, this steady bombardment reshapes the top layer of regolith, making it more fragmented and sharp. The size of micrometeorites ranges from tiny dust particles to larger pebbles. Small particles may penetrate only the top millimeter of regolith, while larger ones can dig several centimeters or more. On steep slopes or loose surfaces, these impacts can dislodge regolith and dust, creating microslides. A small particle can trigger cascading movements of dust and pebbles down slopes, adding further instability to already precarious terrain. The repeated impact of micrometeorites also contributes to regolith formation. Each strike fractures rock, producing small shards and particles. Over billions of years, this process created the thick, abrasive layer of dust and rock fragments that now covers much of the lunar surface. The regolith is a direct result of the constant bombardment, and its properties, sharp, fine, and loose, are shaped by these impacts. Micrometeorites can also alter the chemical and physical properties of the surface. High-speed impacts melt tiny portions of rock and fuse particles together. Glassy spherules form, embedded in the regolith. These particles have sharp edges and can enhance the abrasiveness of dust. The combination of shattered rock and fused glass makes the lunar surface particularly difficult for movement and long-term equipment stability. Because the moon has no atmosphere, there's no weather to erode these features. Craters and impact scars remain intact for millions or even billions of years. The surface gradually accumulates these small craters, making it rough at multiple scales. Even seemingly smooth plains contain countless tiny pits and irregularities, creating challenges for landing, walking, or driving. Micrometeorite impacts also produce heat locally. The kinetic energy of high-speed collisions is converted into thermal energy, briefly melting or vaporizing surface material. While this effect is small, it contributes to the formation of impact glass and alters the microstructure of the regolith. Repeated heating and cooling cycles from these impacts may weaken surface layers, making slopes and crater walls more prone to gradual collapse or erosion. The cumulative effect of micrometeorites is constant. Over long periods, even hard rock surfaces are slowly abraded. Smooth boulders can develop pitting, and fragile rocks may break into smaller fragments. On equipment, repeated microstrikes can degrade solar panels, optics, or external components. Protective coatings are necessary, but even they must withstand continuous, high-speed impacts over the mission duration. Micrometeorites vary in composition. Some are metallic, some silicate, and others contain carbonaceous materials. Metallic particles tend to penetrate more efficiently, while softer particles may flatten on impact, but still create damage through local shock waves. The diversity of particle types contributes to the complexity of surface abrasion and material stress. Impact. Frequency is higher for smaller particles. Tiny dust grains strike more often than larger pebbles, producing a continuous, low-intensity abrasion. Larger impacts are rare but carry more energy, capable of displacing significant regolith or damaging delicate instruments. This spectrum of sizes and energies creates a layered hazard, constant minor wear combined with occasional sudden displacement. Micrometeorite effects are also magnified in certain regions. Elevated surfaces, crater rims, or slopes are more exposed to direct impacts, while depressions may receive less bombardment but accumulate dislodged debris from nearby strikes. Surface orientation relative to incoming particles affects risk. Flat plains receive uniform strikes, while slopes in irregular terrain may experience more concentrated micro-collisions on edges and peaks. Shadowed regions are affected differently. Without sunlight, electrostatic charging is reduced, and dust movement may be slower. However, these areas can still receive particles from nearby impacts or through long trajectories. Particles may bounce, ricochet, or travel significant distances, landing in areas that appear shielded. This adds hidden hazards, even in areas that seem protected from direct exposure. The lack of atmosphere also means that soundless impacts occur. There is no medium to carry vibrations or shock waves as on Earth, so impacts are purely mechanical on the surface. There is no warning of strikes except for instruments that detect vibration or pressure changes. Humans or machinery cannot sense incoming micrometeorites before contact. Over time, micrometeorites contribute to the smoothing of smaller features and the erosion of sharp edges. While new craters form continuously, the repeated impacts wear down protrusions and redistribute fine particles. Slopes gradually lose loose material, terraces may crumble, and dust layers become more uniform. These slow processes create a constantly evolving surface that requires attention for navigation and stability. Micrometeorites also interact with regolith dust. When a particle strikes, it can dislodge fine dust, creating temporary clouds of airborne particles that settle slowly due to low gravity. This can coat equipment, alter traction, or increase mechanical wear. Dust movement from micrometeorite activity is subtle but continuous, affecting both terrain and instruments. In addition to physical hazards, micrometeorites influence scientific measurements. Instruments sensitive to small impacts or surface movement must account for constant micro-collisions. Data collected over time can be affected by sudden particle strikes, requiring calibration or adjustment. Understanding the frequency and scale of micrometeorite impacts is essential for both operational safety and scientific accuracy. The cumulative effect of billions of years of micrometeorite bombardment is a fractured, jagged, and finely divided lunar surface. This process has created the regolith, contributed to crater formation, and shaped every exposed area. The combination of constant small impacts, occasional larger strikes, and the absence of atmospheric protection makes the moon's surface uniquely hazardous. In conclusion, micrometeorite impacts represent a persistent, unavoidable hazard on the moon. They strike constantly, at high speeds, and penetrate the surface without warning. Their effects shape the regolith, wear down materials, and influence terrain stability. Unlike Earth, the moon lacks an atmosphere to filter or slow these particles, leaving equipment, structures, and explorers exposed to continuous micro-collisions and long-term mechanical stress. Understanding these impacts is essential for designing safe exploration systems and ensuring the longevity of any surface mission. The moon is exposed to high levels of radiation because it lacks a global magnetic field and a thick atmosphere. On Earth, the magnetic field and atmosphere block most cosmic rays and charged particles from the sun. On the moon, there is no such protection. Cosmic rays, composed of high energy particles from outside the solar system, strike the surface directly. These particles include protons, electrons, and heavier atomic nuclei. Each impact delivers significant energy to the surface and anything exposed on it. Solar activity also contributes to radiation hazards. The sun emits streams of charged particles, known as the solar wind, continuously. During periods of high solar activity, such as solar flares or coronal mass ejections, the intensity of particle flux can increase dramatically. Solar particle events can deliver doses of radiation hundreds of times higher than the background level in a short period. These bursts of energy can penetrate unshielded equipment and pose serious risks to biological tissue or sensitive electronics. The energy of these particles is significant. Cosmic rays move at nearly the speed of nearly light, carrying enough energy to penetrate several centimeters of rock or metal. Solar energetic particles are slower but still highly charged and capable of ionizing atoms in materials they pass through. Both types of radiation interact with the lunar regolith, sometimes creating secondary radiation in the form of neutrons or gamma rays. This secondary radiation can extend the range of exposure, even in areas partially shielded by dust or rock. Surface exposure is constant on the moon. Without an atmosphere, there is no filtering of sunlight or particles. Areas that are fully illuminated receive direct solar radiation, while shaded or shadowed areas still receive cosmic rays. The only variation comes from local terrain, such as crater walls or boulders, that provide partial shielding. Even within shallow depressions, radiation levels remain high compared to Earth's surface, as there is no substantial natural barrier. Shielding limitations are an important factor in exploration. Planning. Thin metal layers, or regolith, or water, can provide some protection, but effectiveness depends on thickness and density. A few centimeters of metal may reduce low energy particle penetration, but cosmic rays and high energy solar particles can still pass through. Thick layers of regolith, several meters deep, provide better protection, but movement through these areas requires additional engineering. Habitats or protective structures must consider particle flux, duration of exposure, and energy spectrum to ensure adequate safety. Radiation exposure affects both humans and electronics. For humans, high energy particles can damage DNA, increasing the risk of long-term health problems such as cancer. For electronics, energetic particles can cause single-event upsets, damaging circuits, or causing malfunctions. Even shielding designed to reduce risk must account for the full spectrum of particle energies and the possibility of prolonged exposure. Solar particle events are particularly hazardous because they can occur without much warning. Instruments on Earth or in orbit can detect increased activity, but on the moon, any delay in warning means exposure occurs almost immediately. Protective measures, such as retreating to heavily shielded areas or using portable shields, are essential during these events. Long term planning must include both active and passive protection strategies to mitigate cumulative radiation dose. The intensity of cosmic rays varies with solar activity. During solar maximum, the sun's magnetic field partially deflects cosmic rays, reducing their flux. During solar minimum, cosmic ray intensity is higher, and more high energy particles strike the surface. Understanding these cycles is essential for scheduling long duration missions or timing operations to minimize radiation exposure. Radiation penetrates differently through various materials. Regolith provides partial shielding, but thin layers are insufficient against high energy particles. Dense metals, water, or specialized polymers can absorb or scatter particles, reducing penetration. Shielded habitats may incorporate multiple layers to maximize protection while maintaining structural stability. Surface vehicles, instruments, and suits must also balance weight and mobility with shielding requirements. Craters, ridges, and overhangs offer some natural protection. Deep crater walls may block direct sunlight and reduce exposure to solar particles temporarily. However, cosmic rays can penetrate even these structures, and scattered secondary radiation remains a concern. Locations that seem safe visually may still expose explorers to harmful doses, requiring careful assessment of both terrain and shielding. Long term exposure to radiation affects material integrity. Polymers, metals, and composites can degrade under prolonged bombardment from charged particles. Microscopic changes accumulate over time, weakening structures, reducing flexibility, or creating embrittlement. Equipment designed for lunar conditions must account for gradual radiation induced wear, particularly for long duration installations or repeated missions. Radiation also interacts with regolith. High energy particles striking the surface produce secondary radiation and can activate certain minerals, causing local emission of gamma rays or neutrons. This interaction can create additional hazards near the surface, even in areas shielded from direct sunlight. Electronics or scientific instruments must account for background radiation from the regolith itself. The moon's poles present unique radiation conditions. Craters near the poles contain permanently shadowed regions. These areas avoid direct sunlight and solar particle flux during the lunar day, offering cooler temperatures and some reduction in radiation. However, cosmic rays still penetrate, and scattered particles from surrounding surfaces maintain a baseline level of exposure. Shielding in these regions is more effective, but planning must consider both radiation and accessibility. Radiation monitoring is essential for lunar operations. Instruments measure particle flux, energy levels, and cumulative doses. Real time monitoring helps manage risk during solar events and informs habitat design, material selection, and operational procedures. Data collected over multiple lunar days provides insight into long term exposure patterns and helps develop mitigation strategies. Surface operations must balance productivity with radiation risk. Extended time in unshielded areas increases cumulative exposure, while retreat to shielded zones reduces operational efficiency. Planning tasks such as excavation, sample collection, or equipment deployment requires coordination with radiation forecasts and local shielding availability. Even short missions must account for both predictable exposure and sudden solar particle events. Solar activity cycles affect radiation exposure over months and years. Mission planning incorporates predictions of solar maximum and minimum to schedule activities. Longer term installations must consider cumulative doses from both constant cosmic rays and episodic solar particle events. Materials, electronics, and protective designs are tested for durability under these conditions to ensure continued functionality. Radiation interacts with human habitats in multiple ways. Shielded walls reduce particle flux, but openings for airlocks, hatches, and windows create potential weak points. Air circulation, structural design, and material selection must minimize exposure while maintaining habitability. Even small gaps or thin layers can allow particles to penetrate, highlighting the importance of integrated design for safety and operational effectiveness. Radiation also affects scientific instruments. Detectors, cameras, and electronic sensors are susceptible to damage from energetic particles. Background noise from cosmic rays must be filtered from data, and shielding is required to maintain instrument accuracy. Long term experiments may include redundant systems or calibration routines to compensate for cumulative radiation effects. In conclusion, the Moon's lack of magnetic field and atmosphere exposes the surface to continuous cosmic rays and episodic solar particle events. Surface exposure is unavoidable, and shielding provides only partial protection. Radiation affects humans, electronics, materials, and scientific instruments, requiring careful planning for all operations. Understanding the patterns, intensity, and effects of radiation is critical for safe exploration, long duration missions, and the design of protective systems on the lunar surface. The Moon is an environment of extreme scarcity. Unlike Earth, it provides almost no natural resources that humans can use directly. Water is extremely limited, existing mostly as ice in permanently shadowed craters near the poles. Even in these locations, the ice is buried under meters of regolith, mixed with dust, and often located in uneven terrain. Extracting it requires advanced drilling or heating techniques, as simple collection is not possible. Oxygen is not freely available in the lunar environment. The regolith contains oxygen bound in minerals, primarily as oxides in rocks and dust. Releasing oxygen from these minerals requires chemical processing, high heat, and energy input. This means that for any long term habitation, oxygen must either be produced on site using technology or brought from Earth. Natural breathable air does not exist, and any leak or failure in life support systems creates immediate danger. The Moon also lacks a natural atmosphere to moderate temperature or pressure. Surface pressure is effectively zero, which means that any breach of a suit, habitat, or pressurized module can be life threatening within seconds. Humans cannot survive without protective equipment, and small damage from dust, micrometeorites, or mechanical failure can become critical. The isolation and lack of environmental support multiply these risks. Materials for construction are scarce. Metals, polymers, and other structural components must be delivered from Earth, as the Moon does not contain large accessible deposits of refined resources. While regolith can provide some building material through sintering or 3D printing, the process is energy intensive and limited in strength. Simple walls or shielding can be constructed using regolith, but complex structures, airlocks, and machinery still require imported components. Fuel for propulsion, electricity storage, or chemical processes is similarly limited. Hydrogen, needed for fuel or oxygen generation, is not abundant. Energy must come from solar panels or stored power systems, both of which depend on initial materials brought from Earth. Sunlight is available for roughly 14 Earth days at a time, followed by a lunar night of equal length, complicating energy storage and continuity. Environmental isolation compounds all hazards. The Moon is hundreds of thousands of kilometers from Earth, meaning resupply or rescue is not immediate. Any medical emergency, equipment failure, or environmental breach must be addressed on site. Even minor issues can become critical if there is no rapid external support. Isolation increases the importance of redundancy in systems, careful planning, and autonomous problem solving. The combination of resource scarcity and isolation affects planning for human activity. Habitats must be sealed and reliable, with multiple backups for air, water, energy, and waste management. Food cannot be grown without controlled life support systems, and supply shipments from Earth are slow and costly. Equipment must be robust and repairable on site, as replacement parts are not immediately available. Water scarcity affects not only consumption, but also cooling and other industrial processes. Any extraction or recycling system must operate efficiently, as every drop of water is precious. Ice deposits in polar craters may serve as long term sources, but accessing them requires overcoming terrain hazards, temperature extremes, and energy limitations. Water collection is far from straightforward and carries logistical and safety challenges. Oxygen scarcity is equally critical. Air must be produced, stored, and carefully monitored. Habitats must maintain a pressurized environment with redundant life support systems to compensate for leaks or equipment failure. The presence of dust complicates life support, as fine particles can interfere with seals, sensors, and filtration systems. Even small contamination can reduce efficiency and increase risk over time. Food supply relies entirely on what is transported or grown in controlled systems. The moon does not provide natural edible resources. Hydroponic or other artificial systems require water, energy, and nutrients, all of which must be maintained carefully. Equipment failure or nutrient depletion can compromise food production. The lack of natural reserves means that long term habitation requires meticulous management of all consumables. Isolation also affects emergency response. A medical incident, injury, or equipment malfunction must be handled entirely by the crew or through remote guidance. Communication with Earth is delayed by several seconds, and no immediate evacuation is possible. This isolation makes even minor accidents potentially serious, emphasizing the need for self sufficiency and planning for redundancy in all critical systems. The scarcity of energy compounds other risks. Solar panels generate electricity during the lunar day, but the long lunar night requires energy storage. Batteries or other storage systems are finite and subject to wear or damage. Any interruption in energy supply can affect oxygen production, temperature control, communication, and water recycling, creating cascading hazards. Redundant systems are essential to prevent critical failures. The lunar surface itself contributes to isolation. Craters, regolith, steep slopes, and rills make travel slow and hazardous. Moving between different areas, such as from a habitat to a polar ice deposit, is not simple. Even short journeys carry risks of dust infiltration, mechanical failure, and navigation challenges. Terrain features effectively extend isolation by limiting mobility and access to resources. Communication limitations increase isolation further. While radio signals can reach Earth, the moon's far side or deep craters may block direct contact. Relay satellites or specialized equipment are required to maintain continuous communication. In areas where signals are obstructed, crews must rely on autonomous decision making and internal support systems, adding to operational risk. Environmental control systems must address multiple scarcity factors simultaneously. Temperature extremes, a lack of air, and limited water require integrated solutions. Cooling, heating, and pressurization systems are interdependent, meaning that a failure in one area can affect the others. Redundancy, monitoring, and maintenance are critical for safety, as even small lapses can become life threatening. Long term habitation faces cumulative effects of scarcity and isolation. Dust can damage mechanical systems, energy storage is finite, and water and air must be constantly recycled. The environment allows no margin for error. Over time, even minor inefficiencies in system performance can accumulate, creating significant hazards that require careful attention and constant management. Exploration planning must account for resource distribution. Habitats are typically positioned near potential water sources, sunlight exposure, or terrain that allows some natural shielding. Resource scarcity determines location choice, operational schedules, and mission duration. Distance from supply points or energy sources further emphasizes the risks associated with environmental isolation. Isolation also influences a psychological and operational risk. While the moon is uninhabited, humans must function in confined, self contained environments with limited interaction. Delays in communication and resupply increase the consequences of mistakes, equipment failure, or accidents. The lack of immediate external support makes robust training, planning, and redundancy essential for mission safety. In addition, any construction or exploration effort must minimize dependence on external resources. Habitats, vehicles, and instruments need to be designed for maximum efficiency, reuse, and repairability. Regolith may provide partial material support, but it cannot replace critical imported components. Scarcity requires careful management of every consumable, every system, and every movement on the surface. Finally, environmental isolation magnifies all other hazards. Extreme temperatures, radiation, micrometeorite impacts, regolith abrasiveness, and steep terrain each carry risks. In combination with limited water, air, energy, and materials, these factors make survival and long term operation a constant challenge. Mitigation depends on careful design, redundancy, and thorough planning for every foreseeable contingency. Resource scarcity and isolation define the boundaries of human activity on the moon. Without access to sufficient water, oxygen, energy, and materials, every task carries additional risk. Emergency response is limited, mobility is constrained, and any system failure can quickly escalate. Understanding these limits is essential for safe exploration and establishing sustainable operations in a place where the environment offers almost nothing to support life. The moon presents a combination of hazards that together make human activity extremely difficult. Terrain features such as craters, steep slopes, rills, and lava tubes create unstable surfaces that can cause accidents. Small missteps or vehicle mishandling can lead to falls or entrapment, as regolith and dust conceal depressions and loose material. Even carefully chosen landing sites still require constant vigilance due to these hidden dangers. Temperature extremes add another layer of risk. Surface temperatures vary from over 100 degrees Celsius during the lunar day to below minus 170 degrees at night. Equipment must withstand repeated heating and cooling cycles, while habitats and suits must maintain internal conditions suitable for human survival. Rapid or prolonged exposure to these extremes can quickly overwhelm protective systems. Radiation is a persistent hazard. Without an atmosphere or magnetic field, the moon is exposed to cosmic rays and episodic solar particle events. Prolonged exposure increases risks to human health and gradually degrades materials and electronics. Protective shielding is possible, but adds weight, limits mobility, and must be carefully designed to remain effective during long-duration missions. Micrometeorite impacts are constant and unpredictable. Even small particles striking at high velocity can damage equipment, spacecraft surfaces, and protective suits. Over time, repeated impacts contribute to abrasion, punctures, and operational wear. Without atmospheric protection, there is no natural barrier to slow or burn these particles, leaving humans and machinery continuously exposed. Lunar dust creates its own set of hazards. The fine, sharp particles adhere to suits, instruments, and mechanical joints, causing wear and reducing performance. Electrostatic charges allow dust to cling to surfaces, interfering with seals, optics, and moving parts. Dust clouds from human activity or natural disturbances settle slowly, increasing contamination and maintenance needs. Long-term exposure can degrade life support systems and compromise mission safety. Isolation and resource scarcity further increase risk. Water, oxygen, energy, and materials are limited or require advanced extraction and recycling methods. The distance from Earth means no immediate rescue or resupply is possible. Any failure in life, support, equipment, or habitat can rapidly escalate into a critical situation. Apollo missions managed short duration exploration with tightly controlled resources, but extended missions magnify these challenges. Technological and logistical limits during the Apollo era constrained what could be achieved. Spacecraft and suits were designed for brief surface activity. Habitats were non existent, and energy, water, and life support were limited to what could be carried from Earth. Communications were dependent on line of sight, restricting operational range. The cumulative effect of terrain hazards, extreme temperatures, radiation, dust, and micrometeorites made sustained or repeated human presence difficult to justify with available technology. Every mission required careful scheduling to minimize exposure to these hazards. Activities were limited in duration and distance, with astronauts remaining within a few kilometers of the lander. Equipment was designed for short term functionality, not long term durability. This approach reduced risk, but also restricted exploration, preventing extended study or habitation. The moon could be visited, but not easily occupied for long periods with the technology of the time. The cumulative risks create a scenario in which even small problems can have serious consequences. A dust intrusion into a mechanical joint, a micrometeorite puncture in a suit, or an unexpected terrain collapse could cascade into life threatening situations. Protective measures are essential but increase complexity, mass, and operational demands. Every system must be robust, redundant, and carefully monitored to maintain safety. Environmental hazards interact in ways that amplify risk. Temperature extremes can stress materials that are already being abraded by dust. Radiation gradually degrades structural polymers, while micrometeorites create microfractures. Isolated terrain magnifies the consequences of minor errors, as help is distant. Resource scarcity ensures that any failure in supply or recycling cannot be quickly remedied. Together, these factors create an environment in which human activity is highly constrained and potentially dangerous. These factors explain why humans have not returned after Apollo. The technology required for long duration habitation was beyond what was feasible in the 1970s. The cost and complexity of creating safe, sustainable operations exceeded mission budgets. Even short visits carried measurable risk, carefully managed through limited schedules and highly trained crews. Repeated or extended missions would have required new systems for energy, shielding, life support, and mobility that were not yet available. Future missions will need to address the cumulative hazards comprehensively. Advanced shielding for radiation and micrometeorites, dust resistant materials, robust mobility systems, and reliable life support with recycling and resource extraction are all necessary. Habitats must account for thermal extremes, solar exposure, and structural integrity under repeated stress. Energy storage and distribution must handle long lunar nights, while redundancy must cover all critical systems to allow autonomous operation. Exploration planning must integrate environmental risk with logistical capability. Sites must balance access to water, sunlight, and relatively safe terrain. Vehicles must navigate uneven surfaces, avoid crater edges, and carry redundant systems. Life support must handle variable conditions, including solar particle events and micrometeorite exposure. Even with modern technology, the moon remains a place where careful design, preparation, and constant monitoring are essential. The combination of hazards explains why human presence has been brief and carefully managed. The moon can be visited, but long term occupation requires addressing multiple simultaneous challenges. Each hazard, terrain, temperature, radiation, dust, micrometeorites, scarcity, isolation, interacts with the others, increasing the potential for failure. Cumulative risk is a primary consideration for any mission, past or future. Learning from past missions informs future exploration. Robotic reconnaissance, resource mapping, and simulation allow planners to anticipate hazards and design protective systems. Advanced materials, autonomous repair systems, and energy efficient life support may enable longer stays. Still, the environment requires respect for its limits. Human activity on the moon will always involve careful management of risk and resources. In addition to technical solutions, operational protocols are critical. Time outside habitats must be limited and scheduled with respect to radiation and thermal conditions. Dust mitigation procedures must be in place, including cleaning, sealing, and filtering. Micrometeorite risks require structural reinforcement and continuous monitoring. Resource management ensures that water, oxygen, and energy are not exhausted unexpectedly. Ultimately, the reason humans have not returned to the moon is the combination of these factors. No single hazard is insurmountable, but together they create an environment that is difficult to inhabit safely. The Apollo missions demonstrated that short duration exploration is possible, but sustained presence requires technological advances that were not available then and are still challenging today. Understanding these cumulative risks also guides future mission planning. Robotic scouting, habitat testing, and incremental exploration reduce exposure while providing scientific return. Long term habitation will depend on technologies that can handle the abrasive regolith, extreme temperatures, radiation, micrometeorites, and resource limitations simultaneously. Mitigation strategies must address all hazards in concert to ensure both safety and mission success. The moon remains a place of opportunity and challenge. Its surface provides scientific insight and potential resources, but only with careful engineering, planning, and awareness of cumulative hazards. Each mission builds knowledge about the limitations imposed by the environment and the solutions required to overcome them. Sustainable human activity is possible, but it demands respect for the moon's unique combination of dangers. In conclusion, humans never returned after Apollo because the moon is an environment in which multiple hazards converge. Terrain instability, temperature extremes, radiation, dust, micrometeorites, resource scarcity, and isolation all interact. The technology of the Apollo era allowed temporary visits, but not sustained occupation. Future missions must account for these hazards comprehensively to enable safe and extended presence on the lunar surface. The moon is accessible, but only when environmental, technological, and logistical challenges are fully addressed. Even with modern advancements, each mission requires careful planning and system redundancy. Understanding the cumulative effects of the moon's environment remains essential for safety and success. The lessons of the past continue to guide the future of exploration, informing strategies for habitat design, mobility, life support, and risk management. The moon's surface is a record of both opportunity and constraint, showing what is possible while highlighting the limits imposed by natural hazards.